So it's a great honor to be here. Actually, the 3 days ago, I did my presentation in fuel cell at Marrakesh. And today I will give a presentation about zinc battery. So as you know, my research group is mainly focusing on the electrochemical energy. We deal with the fuel cell and also rechargeable zinc air battery, including zinc iodide and zinc manganese oxide battery. So today, and also we do sensor and also lithium battery. Today we were focusing on rechargeable zinc air battery. As you know, we are facing the energy challenge, and we need more and more energy because our population increased very fast. And now at this stage, we rely more on fossil fuel. And we need to go to renewable energy. And I believe, like Morocco is doing, from yesterday's presentation, I heard about this. Here, we have a lot of solar energy people are using. That's very encourageable. And in terms of, in order to use renewable energy, we need a very good energy storage system. Especially like electrochemical energy storage system is a very good medium to make the renewable energy available worldwide, including the solar energy and the wind energy, and also including the transportation. We need a very good battery. So when we talk about battery, electrochemical energy storage system, we have 3 applications: grid energy storage, transportation, and a portable electronic device application. In terms of these 3 applications, when we deal with electrochemical energy system, battery, we have different kind of battery available, like lithium battery, already widely used. And now we try to go to higher energy. And in terms of my topic is mainly focusing on zinc. Why zinc, battery is very important? I was thinking, we try to, if we compare, these metal together first, like a zinc metal with lithium, sodium, aluminum. And then now people try to using, metal air battery directly. So you can use the metal as an anode directly. However, if you compare with these, different metals, I think, the zinc has a pretty good advantages. You see, the zinc, number 1, is low cost. Number 2 is very safe. Even you contact with water or air, it's no problem. However, if you go to the lithium, maybe it's more expensive and also not very stable. It's not safe when you use it. And compare with sodium, sodium and lithium are very similar. And compare with aluminum, also, the zinc much easier to for the reaction also, compared with the aluminum. So with this advantage, we believe zinc battery will have a big future. In terms of zinc battery, there are different kind of zinc battery available, like zinc ion battery, that a lot of researchers are doing it. Zinc air battery, today we will mainly put effort onto zinc air battery. And zinc flow battery, like different kind of zinc match with iron or zinc match with iodide, and a hybrid zinc battery. So these are the current zinc battery technology that people are doing the research at this stage. And when we go to zinc battery, we'll go to more specific. First, zinc battery has pretty high energy density. So you think about actually for the when people using the hearing aid system, typically they use zinc, primary zinc battery. The energy density is above 1,000 watt-hour per kilogram. So which means in the practical already shows the energy density is much higher than the lithium battery. However, that one is not rechargeable yet. And also it's environment friendly. And the third is, it's very safe and inexpensive. And we have large zinc deposits around the world, including like in Canada and the United States. With this advantage, why until now we still didn't see the rechargeable zinc battery available in the market? I believe the main reason is we have 3 challenges related to the zinc battery. First is zinc electrode. As you know, for all the metal air battery, when you deal with the metal in the anode, there is a dendrite challenge. So how to suppress the zinc dendrite formation during charge-discharge is one important topic. And another is the electrolyte. Because in the zinc air battery, at this stage, people typically using the aqueous electrolyte, using the alkaline electrolyte. So which means if there is CO, as we know in the air, there is a tiny, very low concentration CO2 exist. So how the CO2 will affect the electrolyte, then degrade the performance. That is another challenge we need to solve. And the third challenge is air electrode. Air electrode, which means related, because for rechargeable zinc battery, it's related to the charging and the discharge. During the charging, it's oxygen evolution reaction. During the discharge, it's oxygen reduction reaction. So which means we have to find a good catalyst for these 2 reactions during charge-discharge. So we need a very good bifunctional catalyst to improve the performance and have good stability, cyclability. So for today's talk, we will mainly talk about in the past 10 years in our group, how did we solve this problem? So in order, as we mentioned, for the zinc battery, we have 2 reactions at the air electrode. During discharge is ORR. During charging is OER. So we need bifunctional catalyst. So it's more complicated than the fuel cell. Fuel cell is only ORR, discharge. So for this, we need charging also. So commonly, actually, the precious metal catalyst like platinum or iridium, these catalysts will be suitable for OR or OER. And typically, they are more stable. However, these are too expensive. If we want to have low-cost rechargeable zinc battery available for the market, we'd better not using the expensive metals. So in terms of that one, we try to try to use a non-precious transition metal to meet this requirement. So when we try to design a good bifunctional catalyst, as we know, we have these 4 parameters we need to be careful. One is we'd better have a high surface area catalyst so that you have enough active sites available during operation, right? Second is you'd better have an optimal oxygen adsorption energy because this will relate to your kinetic very closely. And then number 3 is for all the electrochemical catalyst, you'd better have very high conductivity. With this high conductivity, you make this reaction easier. And then number 4 is stability. Because for all these reactions, during charge and discharge, it's from low voltage to high voltage, which means corrosion happens very fast. If your catalyst is not stable, then the battery, the lifetime will be short, right? So we have to meet these 4 requirements in order to design a good bifunctional catalyst. So when we try to design this catalyst, at the beginning, available is always bulk materials. However, as we know, bulk materials we don't have a high surface area, so we need to go to nano. So when we go to nano materials, actually, when we try to use it, we found that it's not easy to fabricate into the electrode if you use nano. So finally, we have to combine these into nanostructured materials. So these actually nanostructured materials may be it still looks like a particle, but the particle size will be more than micrometer size. So easy to fabricate an electrode. However, it still has high surface area so that you can meet the requirement for the catalyst. Have enough active sites. So with this, in the past, actually, 10 years, we initiated the zinc rechargeable zinc battery project in 2009. Then in the past years, we tried to, based on the design regulation, one direction is we try to increase mass activity. The other is increase specific activity, so related to the intrinsic kinetics. Then finally, we try to combine these together, construct a three-dimensional catalyst or electrode, so that it can meet the requirement for the rechargeable zinc battery. So, for example, the first work we did is we tried to because this is for bifunctional catalyst. When we try to design, we try to using the lithium nickel oxide. This could be a good OER catalyst for the charging. And the nitrogen doped carbon nanotube actually, it's proved it's a good ORI, has good ORI activity, so it's suitable for discharge. So at the beginning in 2009, we tried to combine these two materials together, and so that we can have excellent OER activity, excellent ORI activity, and very good stability. And we are not just physically mixing. We try to synthesize together. So the way we do is we try to have the lithium nickel oxide nanoparticle first. Then on the surface, we grow by the CVD methodology. We grow the nitrogen doped carbon nanotube on the surface of this particle. And here we call it, this is a coronal structure catalyst. So at that time, we successfully synthesized this kind of catalyst, and we made a homemade zinc battery at that time because there is no standard cell available at that stage. So we successfully actually at the beginning we checked the discharging performance. So if you compare the discharge, you see that actually our designed catalyst we call the CCBC. So CCBC showed it's the black one. It shows similar discharge performance with the platinum. Because as you know, carbon-supported platinum is the best OR discharge catalyst, OR catalyst. For the charging, we also compare with the iridium. Iridium is proved to be a very good commercial, OER catalyst, charge catalyst. So which means is our designed catalyst has a similar discharge performance with platinum and a similar charging performance with iridium. So which means it's have a pretty good activity. So in terms of the charge, when we do the cycling, we found that actually it's much more stable than the commercial, just the carbon-supported platinum and the carbon-supported iridium. Because the carbon-supported platinum and the carbon-supported iridium, these two commercial catalysts, they are not designed for the bifunctional catalyst application. And we found that because of this carbon problem, degradation happened very fast. So after this platinum, you only can last about 15 or 16 hours and gone. And similar like iridium. And for our bifunctional catalyst, we cycled more. We did more cycling. Actually, even after 1,000 cycles, it's still stable. So with this catalyst, based on this, after recently we also designed some other type of catalyst. Like this catalyst with another catalyst is by this synthesis methodology, we successfully can get porous graphene it's doped porous graphene with cobalt, with chalcogen tailored oxygen catalyst. So the porous graphene itself has defects. These oxygen defects also will provide activity, and because it's porous, will make the the mass transport easier during the reaction. So with this catalyst, we also successful. If you take a look at this is a half cell, right? The onset potential is good, and this is a OER, also half cell. And definitely this is, if you take a look at the SEM, you can see the pore was created, and a lot of defects exist. It's proved by the XPS and the ELNES. And with this, if you do we checked in the zinc battery, cell, you can see our, this type of non-precious this kind of bifunctional catalyst is also very stable, and the resistance is pretty small. And that is only, the catalyst itself. The next step, actually, we try go to the, it's a three-dimensional, as we mentioned. So this three-dimensional is, we use, we designed, the like 3DOM catalyst. It's the pore is, we have a big pores. It's about 50 nanometer or 100 nanometer. You can design it, just depends on what's the templates you are using. You can control the PS beads size, then you can control the pore. So with this catalyst, we can easily design, 3DOM catalyst, so that you can have a good micrometer size catalyst, and or have a very good porosity inside, so that you can have very good mass transport in the catalyst. That is our main purpose. So you can see this. This pore is well controlled when you prepare the catalyst. So with this catalyst also, we prove this is very stable, because for this catalyst, you even don't need using carbon inside. We can use the titanium nitride and with some other metal like cobalt together. So because as you know, like titanium nitride is very conductive itself and is more durable than the carbon during the charge and discharge. So that's a new type of catalyst we design. We even don't need, we will not involve any carbon inside. So this we will bypass maybe quickly. And another way actually we design the catalyst is, I would introduce, is air electrode design. Air electrode design actually, as we know, for the traditional catalyst is particle. So which means we will have to coat this catalyst with bind together or conductive polymer together, then coat it onto the current collector or gas diffusion layer with. However, at the same time, we think this maybe is not the best way. So another good way we are trying is we try to grow the catalyst onto this, the substrate, current collector directly. So here, actually, one methodology we're using is we're using metal mesh directly, and then you grow the cobalt oxide nanowire directly onto the metal mesh. Then you can use this as electrode directly. So if you take a look, we use this electrode we can make, by the stainless steel mesh. After it grows the cobalt nanowire, actually the color become black. And if you go to the SEM, you can see clearly, actually, this is just metal mesh. And after synthesis, you can control the time or the concentration. Then you can control the length of the cobalt oxide nanowire, and you can control the loading of the catalyst of onto this metal mesh. And we also test the performance. It's pretty reasonable. And especially, for this one, the impedance, by the impedance analysis, we can see the resistance is pretty small compared with other. And also the cyclability is very good for this electrode. So for this electrode, which means, you can easily fabricate. And also when you use it, because you use metal mesh as the support, so it's flexible and strong, So based on that, after that, we further, try to improve the performance. So the other methodology we're using is we have the metal mesh, we have the nitrogen doped carbon nanotube with the cobalt oxide nanoparticle together, and also grow onto the metal mesh. So this we have introduced another thing is a nitrogen doped carbon nanotube. It's like here, So this with this one as we grow, this nitrogen doped carbon nanotube and with the cobalt oxide particle on the surface. And with this one, actually, we prove that actually is successfully, by successfully, we confirm that it's very homogeneous. And also, we confirm the performance by the half cell and the full cell. So by the full cell, we can see, okay, with this new type of electrode, it's very stable and the performance is further improved actually compared with the previous one. So when we design the catalyst, actually before it's focusing on the materials itself. But at the same time, now actually we try to understand how these active sites really work during the cycling, during charge discharge, during OR or OER. So we try to combine with the model like DFT calculation. Like this one, actually, we calculated the oxygen vacancy, how this oxygen vacancy will affect the activity. And we also, as we mentioned, we try to go to the single atom catalyst research so that we can more accurately design the active sites and control the active sites and control active sites density so that you can design better catalyst. That's the purpose, Like we actually collaborated with a modeling guy, do the DFT calculation, for different active sites so that help us to understand, which one is better. And also, furtherly, actually, we are trying to do more in situ characterization. Like, actually, this we do with a Canadian light source and also including the Argonne National Laboratory. Try to do more in situ analysis to understand what's going on, for this catalyst, so that we can, have a better design. Our goal actually at this stage is still use, for the electrolyte, I'll just mention a little bit. We are focusing on the aqueous and also semi-aqueous, semi-solid, you can say. But in the future direction, I believe, if we want to solve the electrolyte problem, maybe some application we need to go to solid. Actually, we also put a lot of effort into the electrolyte research. And here we will not talk too much. So which means in the past 10 years, based on today's talk, actually, for the bifunctional catalyst air electrode, I think we are ready. We solved that problem, and we can easily scale up by one of these methodologies we are using. And for the zinc electrode, also we try to put a lot of effort to suppress the zinc dendrite formation. And we found some, very useful methodology. We found we can suppress the zinc dendrite formation successfully, and the zinc electrode could last for more than like 1,000 cycles. So which means the zinc electrode now is also almost we solved the problem. And today we didn't introduce here because of time limitation. And now we put more effort into the electrolyte, actually. We try to solve more the challenge facing on the electrolyte. And I believe, with this, if we can solve all the electrolyte problem, then combined with the system design, I believe, this technology could be available for the market in the future. That's our purpose. I believe, for the rechargeable zinc battery, so there's a potential application for flow battery. For the flow battery, maybe you can use for the energy storage for like a grader, nano grader, or micro grader, or large grade. And based on its advantage of high energy density. Also, I believe there is, if we can have a good lifetime cyclability, so it is possible, combine with the lithium battery or whatever, use in the transportation in the future. That's our goal. And also, we can design, flexible battery in the future for this zinc battery. And in our Waterloo, actually, we have a team, actually, electric vehicle team, including fuel cell vehicle team. Actually, we try to, combine like a zinc battery with a lithium battery together so that you can easily increase the energy density. Because as you know, most people every day only drive less than 80 kilometers. So if you use zinc battery as combined with lithium battery, most time you just using lithium battery. You can meet the target. If you drive long distance, you can use a zinc battery. Then in terms of that, the lifetime, the cyclability, requirement for zinc battery will not, don't need to be that high. So which means only several hundred cycles so you can meet that requirement. So we did some calculation with modeling with General Motors together. And that's the idea we think could work in the future. So in the past 10 years, actually, we did a lot of effort. We solved the catalyst problem. We solved the zinc dendrite problem, but definitely zinc dendrite zinc electrolyte still need to be further improved. And now we're trying to go to the demonstration. Actually, we did the demonstration this year. It's a scale up. And also, I would say, I'm from University of Waterloo. It's in Canada. It's we have a lot of water actually. We are in the middle part of these three big lakes. It's 1 hour from Toronto, and I hope in the future you can visit Waterloo. And but it's better to visit in the summertime. But if you want to enjoy snow, you'd better visit December. That's good, So this is University of Waterloo. It's a more engineering school. We are the largest engineering school in Canada. And also, thank you. I really appreciate my team, at Waterloo. And thank you for your attention.